This is our mission. It won't be here.
Yes, it was.
Okay.
Like,
They're just trying to say.
Yes. Okay. Thanks. Okay. We ended yesterday with substitution. Okay, so now we're going to go on to another method that we can use in order to solve our systems of equations. This is actually my preferred method. If I were to choose a method to use, I would usually choose elimination. I just like it better than substitution. But I know some people really like substitution. They like to be able to work with it that way. So you can always go with either one. There's just going to be situations where maybe it is easier to use elimination versus substitution, or vice versa. There are times where it is easier just to use substitution than to try to do elimination. When you're using elimination, this time, unlike substitution, we don't want to solve for one of the variables. We don't want it to say y equals all the other stuff or x equals the stuff. We want them to be lined up where you have your x's, your y's, and your numbers. Okay, so that's this form right here, this ax plus by equals c. We want both of our equations to be in that form. And then you want one of your letters, the x's or the y's, it doesn't really matter, but you want them to have the same number in front. So you want those coefficients to match. It works best if you can get them to be the same number, but opposite signs. If they're not opposite signs, it's fine because we can still work with that. Okay, but I usually like to have them be opposite signs because then I can add my equations together. It'll get those terms that were like, cross them off, and then you get rid of one of the variables and you solve for the other one. Okay, so let's take a look at an example here. Starting with this set of equations, we've got 3x plus 2y equals 4. We've got y equals negative 2x plus 1. The first thing that they did is they rewrote the second equation to get it to be x, y, and then your numbers. So they did that by moving the 2x back over to the left-hand side. And that's how we get this one. They just wrote it first instead of writing it second. But so that equation becomes 2x now, because we add that over to the other side, plus the y equals 1. And they brought down the original top equation. They didn't have to change anything on that one because it already was set up with my x, my y, and my number. So now that I look at this set, this is what I want to focus on for my elimination. Now I want to get either my x's to match or I want to get my y's to match. Again, it doesn't really matter which one you get to match, but I would look for what's the easiest situation. Is there a way to multiply just one of the equations by something instead of both to get the x's or the y's to match? Yeah, what can we multiply by? Yeah, let's take this top equation times a 2. Now, if you guys are okay with that, I'm actually going to take it times a negative 2 because right now my y's are both positive. If I can change that top one to a negative, they'll be opposite signs. So when I add my equations, they'll eliminate. Now, you don't have to do that. You would just, instead of adding, you'd have to subtract your equations. I like to add more so than subtracting because when we subtract, sometimes we miss negative signs, we make mistakes. Adding is usually easier. So I'm going to add these together after I multiply by negative 2. So if I take that top equation, all of it times a negative 2, it now says negative 4x minus 2y equals negative 2. You have to take all the terms times the number that you're multiplying by. And we leave the bottom equation as is. Okay, now what I'm going to do is add these equations together. I'm just going to put a plus sign and like draw almost like you're adding, old school elementary style. We're lining them up and we're adding them in columns. My y's are going to cancel. That's the whole reason why I did that. And I have to add my other terms. What's a negative 4x plus 3x? Negative 1x or just negative x. And what's negative 2 plus 4? Not 0.
Oh, no, sorry. That's the
2. Okay, I can't keep x negative, so we have to switch its sign. So it just becomes negative 2. There's your x. Now with elimination, you will have to still do a little bit of substitution because we have to figure out one of the variables, which we just did, but now we got to plug it back in to find the other one. This is like what we did yesterday though, or even on our bell ringer. It doesn't matter what equation you guys go back into when you're substituting your value back in. So do you guys want to take this negative 2, and if I'm coming back up here to my original equations, which one would you guys rather plug it back into? The second one. So the second one says y equals negative 2x plus 1. So I'm going to rewrite that as negative 2 times negative 2 plus 1. And what's my y going to come out to be? 5. How would I write my final answer? Good. Negative 2 comma 5. Then again, you could check your solution. You could take that solution that you found. You could plug it back into both equations, make sure it balances out like we were starting with yesterday. That would be something that I would maybe do, especially if I had a test on this and I wanted to make sure I was doing it correctly and I got the right ordered pair. Do you have questions on that elimination process? Okay, so turn the page over and I'd like you guys to try this one. Use elimination. See what you can do here. Do we have an answer out there? Something you feel good about? No? What letter did you guys get rid of first, X or Y? Y? What did you do to get rid of your Y's, Breck?
At the bottom, but negative 2.
Okay. So if we multiply the bottom equation by negative 2, it should say negative 2x plus 4y equals 6. And then what'd you do?
Added. Got 3x and then 50.
Good. So x is 5. Okay. Now we're going to plug this back in to solve for either equation to solve for your y. Which one would you guys like me to go back into? Top or bottom? Well, I've heard 2 votes for the bottom, 1 for the top. I think it doesn't really matter which one you guys go back into, because this would be 5 minus 2y equals negative 3. Or if you do this one, it would be 5 times 5 minus 4y equals 9. You plug it in either one, you should get the same answer. What do you get? 4. So your final answer should be 5, 4. Good. Okay, so going forward, there might be times where I ask for you to use a specific method, so just make sure, especially on a test, I know there's one that will say use substitution here, use elimination here. I want to see you use both methods. If I don't specify or a problem doesn't specify how they want you to solve it, it's up to you to decide. What would you rather do? And you could then choose your method of like preference, or you could choose the one that you think would be easiest. Now, all of those situations that we've talked about so far are the cases where the lines do cross and they intersect at one point. But there's going to be situations where you have lines that don't ever cross, or maybe they do, but like in a really unique way. So there's going to be situations down like these next two on the graphs, like here and here. This one is what we've been working with. Okay, the one that I circled, that's the kind that we've been solving for when we've been practicing with our substitution and elimination. But the second two pictures are showing you these cases that are maybe a little more like obscure. You're not going to run into them a ton, but you do see them every once in a while. Parallel lines would be two different equations, but they have the same slope. They have different y-intercepts. Parallel lines would never cross, so there would be no solution that actually satisfies those two lines because they would never intersect with each other. The third situation is infinitely many because you're basically graphing the same line twice. You're putting a line on top of itself. So if you have the same line or the same equation both times, then really what that means is they would share all their points because they would have everything in common. You may not be able to like recognize it just by looking at a problem because they can disguise these a little bit by, making one of the equations take it times a number to kind of distort the picture a little bit. So as you get really good at recognizing these, some of you might be able to like reduce fractions or reduce numbers in your problems and like see, oh, those are actually the same equation or they have similar parts to them. If you can't though, we can still rely on those methods that we've been talking about to solve these. For example, if I'm looking at this one, I would choose, do I want to use substitution or elimination here? When I look at it and I'm trying to decide what would be easier, do any of my x's or y's stand alone? Like, do any of them have just a 1 sitting in front of it? No, they all have numbers. To me, that usually means substitution would involve a process like this that we did on your bell ringer, and I'm going to avoid that if I can. So I'm going to probably use elimination instead. Do you guys want to get your x's or your y's to match? Okay, how would you like to do that? So we'll take the top times the 2. What would the new top equation say? And I'm just going to rewrite the bottom equation. If you were going to get rid of the y's, what would you have multiplied by? A 2 as well, right? So in this case, it doesn't really matter which one you got rid of because what's going to happen on the left-hand side? They're all going to cancel. I'm going to add these together. The x's are gone and the y's are gone. So this is a big 0. But on the other side, what's 8 plus 7? 15. That's all right. Is that true? No. When you get a situation like this where your x's and your y's disappear because they eliminate each other in the same step, and you're left with a false statement, this means that you're dealing with parallel lines. This is a no solution. That means there's no combination of an x or a y that would work. It would be unbalanced for at least one of the equations, if not both of them. So you would have to say no solution on that. Now, if you take a look at the second one here, I think it might be easier on this one. Maybe let's try substitution. Do you guys see why I wanted to use substitution instead? Yeah, the x is by itself. So I'm going to plug this in down below. So I'm going to take this piece, 4y minus 8. I'm going to plug that in for the x on the second equation. So it's right after that 5. Okay, what's going to happen here? I'm going to distribute. What's it say when I distribute? Okay, what happens next? What cancels out?
20. 40 would too. No.
Well,
But we don't want to add the formula.
if you add, well, but if you do add it, okay, that's a good point though. Right now it says this, right? If we did add it, wouldn't it be 0 equals 0?
Yeah.
Yeah, so if you add 40, you still get a true statement, don't you? So it's true this time, which means this would have infinitely many solutions. You're dealing with the same line here. So I'm going to say infinite solutions. You guys could draw me the infinity sign if you wanted to, if you don't want to write all that out. But you are working with the same line stacked on top of itself. All right. Any questions right now on those different situations that we've talked about? Okay, go ahead and turn your page. Just gotta plug my computer in really quick.
That was.
Okay, we're going to take a look at still using substitution and elimination, but now starting to apply it to some problems. So this first one says that a company that manufactures running shoes has a fixed cost of $300,000. So that could be like at $300,000, that's what they have to pay for people to like get the materials, to run their warehouse, their operations, all that stuff. Additionally, it costs $30 to produce each pair of shoes. They are sold at $80 per pair. We're comparing two things here. One's going to be called the cost function and one's the revenue function. Cost is going to be how much the business has to put in and like clear to be in the green. Revenue is going to be how much then profit they would make. So after they pay all their bills and their employees and all that stuff, how much are they taking in at profit for themselves? To write a cost function, we have to think about their fixed cost that they give us and then how much they're selling these or how much it costs to produce the item. So in this case, they're saying that it costs them $300,000 regardless of what they sell, but it does cost $30 to produce each pair of shoes. So for my cost function, I'm going to say C of X for my cost function. I would take that cost per product, like 30. That's my slope. I'm going to put that in front of my X, and I'm going to add on 300,000. Okay, so X represents the number of shoes. So if they produced 100 shoes, we would take 30 times 100, add the 300,000. That would give them like you must get this much money back in order to break even. Now the revenue function is, well, they're selling the product. Okay, you always want to sell your product for more than it costs you to make it because that's how you make money. So to make your revenue function, we'll use R for that. They're telling us that it costs $80 to buy a pair of shoes from this company. So I'm going to write that as 80x. They want to know where's the break-even point. Like how many pairs of shoes does this company need to produce and sell in order to break even and be 0 equals 0? So to do that, you're going to take these two equations that we wrote, you're going to set them equal to each other, and we're going to solve for x. So we're going to take 30x plus 300,000, and we're going to set that equal to 80x. How would you guys solve this? Okay, so I have 300,000 equals 50x. Then you would divide by 50. So go ahead and do that and tell me how many pairs of shoes these people need to make and sell. If you needed to, you could make it a little simpler. You could cross off a 0, and then you could take 30,000 divided by 5, if that's any simpler. Anyone have an answer? 6,000. So they need to sell 6,000 pairs of shoes to break even. So they're producing 6,000 pairs. They also have to sell 6,000 pairs of shoes as well. Anything above that is going to start giving them a profit. Anything below 6,000, they're going to start going in the red. Okay, so I would like you guys to read the next one. It's very similar. I want you to find this company's break even on selling donuts. Okay, there's your two equations that you hopefully were able to write down. You should have set them equal to each other and solve for x. What'd you guys get? 8,000. So here's what that means in the context of the problem. Because there's, how many are they selling like at a time? A dozen, right? They're selling a dozen at a time. So they need 8,000 dozen donuts. How many donuts would that be? Actually, 16,000. Well, no, what's 8 times 12? Be 96,000. So they have to make 90. They have to produce 96,000 individual donuts and sell them all. That's a lot of donuts. Okay. We do have like one last thing to talk about. We can power through it today if you'd like, or we can do it tomorrow.
Tomorrow's gonna be a great day.
Okay. All right. We'll come back to this tomorrow.